Let's talk about a group of chemicals that are true chameleons. I mean, they're everywhere and they're responsible for some of the most wonderful sensations we know.
Just take a second and think about that warm, comforting smell of vanilla, or the spicy, festive scent of cinnamon, right? Those distinct aromas come from specific molecules that are part of this amazing chemical family we're diving into.
But here's the twist. Flip the coin completely, and you'll find they're also responsible for that sharp, really pungent smell of formaldehyde. You know, the stuff used to preserve specimens in a biology lab? So beautiful and, well, industrial, all from the same family.
So what is this chemical powerhouse? How can it be in our favorite desserts, our perfumes, our toughest plastics, and our science labs? All right, let's get into it and uncover the secret behind this incredibly versatile group of molecules.
The secret to all of this, it all comes down to one simple but seriously powerful little arrangement of atoms. Let's meet the star of our show, the carbonyl group.
And here it is. Yep, that's it. Just a carbon atom sharing a double bond with an oxygen atom. It might not look like a big deal, right? But trust me, this little setup is one of the most important players in all of organic chemistry. Its unique personality is the reason for everything we're about to see. See, there's a secret power struggle going on in that bond. Oxygen is what chemists call electronegative. Basically, it's super greedy for electrons, so it pulls the shared electrons in that double bond a little closer to itself. This makes the oxygen slightly negative, and it leaves the carbon slightly positive.
And this tiny imbalance of charge, this polarity, turns the whole group into a magnet for chemical reactions. That slightly positive carbon is like a big flashing "attack here" sign for electron-rich molecules. Meanwhile, the slightly negative oxygen is looking to react with anything that's electron-poor. It's this two-faced nature that makes it such an amazing building.
Okay, so we've got our super versatile building block. What's the first thing we can make with it? Well, we get two major families right off the bat, aldehydes and ketones.
Now, the difference between them is incredibly simple, but it changes everything. It's all about what that main carbon is holding on to. If it's got at least one hydrogen atom attached, bam, you've got an aldehyde. But if it's squeezed between two other carbon atoms, well, that's a ketone.
And you already know these, I promise. Ethanol, also called acetaldehyde, might not ring a bell, but it's a huge industrial chemical. And propanone? That's just the fancy scientific name for acetone. You know, the stuff in nail polish remover.
Now, even with that tiny structural difference, their behavior is worlds apart. Aldehydes are way, way more reactive. So why is that? Well, think of that little hydrogen on an aldehyde. It basically leaves the main carbon atom exposed and ready for action. In a ketone, that same carbon is crowded and shielded by two bulkier carbon groups. It's like a quarterback protected by two huge bodyguards. It's just a much harder target to get to.
And this difference in reactivity, it's not just some cool piece of trivia. Chemists actually use it to their advantage, especially when they need to figure out which one of these compounds they're dealing with.
And one of the coolest ways to do that is the Tollens test. Seriously, this is like a magic trick. You add this special solution called Tollens reagent, gently warm it up, and if you have an aldehyde, it reacts like crazy. And pure, solid silver just appears, coating the inside of the test tube with a beautiful mirror. It's amazing. Ketones, they're too tough, they won't react. So you get that silver mirror, you know for sure you've got an aldehyde. Simple as that.
So that high reactivity of aldehydes, it leads us straight to the next evolution. The third, and you could argue the most important member of our carbonyl family, the super powerful carboxylic acids.
And once again, the change is so simple, it's elegant. You take our hero carbonyl group and you just snap on a hydroxyl group. That's an OH right onto the carbonyl carbon. This combination creates a brand new powerhouse group called the carboxyl group, and that is the signature of every single carboxylic acid.
And just like the others, these are all around us, and their names often tell you their life story. Formic acid, that's the irritant in red ant stings. Formica is Latin for ant. Acetic acid, that's the sharp kick you get from vinegar. And butyric acid, well, that's the unmistakable, not so pleasant smell of butter that's gone bad. Which brings us to their main claim to fame. The name kind of gives it away, right? Carboxylic acids. But what actually makes them acidic?
The whole secret is stability. See, when an acid does its job, it gives away a proton, which leaves it with a negative charge.
In a carboxylic acid, that charge isn't just stuck on one oxygen atom. No way. It gets shared or delocalized across both oxygen atoms through something called resonance. It's like a game of hot potato. By constantly passing that negative charge back and forth, neither atom has to bear the full burden. This makes the whole molecule incredibly stable. And because the result is so stable and comfy, the molecule is more than happy to give up that proton in the first place.
All right, so we've met the whole family: aldehydes, ketones, and carboxylic acids. Cool chemistry for sure. But so what? Why should you care? Well, let's connect all of this back to your world.
Remember that sharp preservative smell we started with? That's formalin. And it's really just a 40% solution of formaldehyde, the simplest possible aldehyde, in water. An incredibly powerful and useful tool for scientists.
And these things are absolute titans of industry. Acetone is a workhorse solvent in countless factories. Formaldehyde is a critical building block for making super strong plastics like bakelite and powerful glues. And a carboxylic acid, hexanidioic acid, is essential for making nylon 6,6. Yep, the stuff that's probably in your carpet or your clothes. And of course, we come full circle back to the wonderful smells and tastes we love. Vanillin, cinnamaldehyde, benzaldehyde, these molecules aren't just found in nature anymore. They're manufactured by the ton to give so many products in the food and perfume industries those amazing, familiar aromas.
They even show up on the ingredient lists of your food. Ever seen sodium benzoate in the fine print? That's just a salt made from a carboxylic acid. Its job is to stop mold and bacteria from growing, keeping all sorts of products fresh on the shelf for longer.
So there you have it. From the fragrance of a vanilla bean, to the fabric in your jacket, to the food on your table. The chemical chameleon at the heart of it all is the carbonyl group. It's a fundamental building block for both nature and our modern world. So the real question is, now that you know its signature, where are you going to spot it next?